And now let me introduce you to Charles Papin. He's a product line manager for CryptoNext. You can take one microphone. He's focusing on post-quantum migration. He graduated from Polytechnique and Centrale Supélec with a specialization in cybersecurity. And he also worked for 3 years at the French Ministry of the Armed Forces. He's today here to present Post-Quantum Cryptography, the subject, the key issues and applications in embedded systems and satellites. Thank you. A great presentation.
Work? Can you hear me? Yes? Great. This one. Okay. So hello everyone. Very pleased to be here to talk about post-quantum cryptography. So we have had quite a great introduction of this topic in the previous show. So I'll try to add our expertise to what has just been said. So we are going to particularly talk about PQC for embedded systems, of course, as we are here at CYSAT. And we'll try to see what are the challenges that come with the rise and the implementation of PQC. Here's our agenda, a little word about post-quantum cryptography and the timeline of its implementation, its standardization, and the threat which is coming, which is the quantum threat. And then we'll see two practical cases where we have to try to implement our post-quantum library within constrained systems. And we'll see interesting results about side channel attacks resistance, along with performance, questions of performance. I know that there was a question lately on this topic, so we'll see what we got here. Okay, just a few words about the company I represent today. So CryptoNext Security, we are hosted just a few blocks away, so we come here as neighbors. We are identified as a pioneer in post-quantum cryptography, building on more than 20 years of academic research. And we are very active into all the standardization processes at the IETF and also at the NIST, for instance. We've been a few days ago, granted the CAVP validation by the NIST, meaning that we are today the only provider of post-quantum library in the European Union that has all the 3 standardized algorithms validated by the NIST. That's the latest news. And we have some proven deployments in many segments of the industry. Banking, of course, defense, public sector, energy, and aerospace, with 2 projects for the CNES and MBDA. Okay, so that was for the corporate presentation. Let's move on to the challenges that are ahead. So basically, post-quantum cryptography. So this, you may understand what it is. It's a quantum computer. Basically, it's a big fridge, right? Trying to lower down the temperature down to 0 Kelvin. And in this little place there, you've got some particles that obey the laws of quantum mechanics, and that are somehow able to compute things in a different way, not a better way, but a different way. And unfortunately, this way of computing is dramatically good at breaking the public key crypto systems that we know today, RSA and the elliptic curve cryptography. So that was the groundbreaking work by Shores in 1994. And so we are really talking about broken crypto systems and not just weakened crypto system, right? What used to take millions of years to infer the private key from a public key in RSA or ECC will now take minutes, all right? So it's just broken dead. So what do we do? Basically, you have the quantum threat here caused by a quantum computer, and then you have to see whether you are in the symmetric or asymmetric case. Symmetric, well, at the beginning you had this Grover algorithm, which states that it's going to accelerate the resolution of symmetric primitives like AES. Thing is, as things go by, we see that Some agencies recommend to double the size of the key. Some agencies just don't, just say that Grover algorithm is not applicable in practice. Well, if you're French and European, you will have to double the size of the key, but not too much of a problem, right? The crypto system remains secure. If you're in the asymmetric case, then again, the crypto system is just broken down, and so you have two quantum safe solutions, either PQC or QKD. For the time being, PQC is the only quantum safe solution that is industrialized, okay, where you don't have any new challenges to make sure it can be adopted by the industry. It's already there, you have standards, the industry is already implementing it like Google, and so it's a quantum safe solution for now, whereas QKD has still some challenges to overcome. Okay, just a slide to show that before we were in a great state where you only had to be resistant to classical computers. Then quantum cryptanalysis came up, mainly with Shor's algorithm, right? And we are in this phase here where a quantum computer has not yet been unveiled, but we still know the capacities that such a computer would have. And in the next few years, we will be in that phase where we'll have to be secure against both classical attacks and quantum attacks. Just also at the bottom here, you see the deployment of the different crypto systems, publicly crypto systems. And I just wanted to mention that all of them, both those based on the traditional problems like RSA, Diffie-Hellman, and elliptic curve cryptography, are as old as the ones that are at the base, at the bottom of the post-quantum cryptography, right? If you look error correction codes, like HQC, for instance, lattices or hash-based cryptography, those are problems that have been studied for quite some time. But the thing is that today, as they become the new standards, there's a lot more money funneled into the academic research, and that is why we have new standards, new research, new results in that field, whereas before we could just rely on RSA and elliptic curve cryptography. Okay, moving on. So you may have already seen this timeline. That's basically the standardization timeline. What's important to see are to look at are the orange case boxes. So the NIST has done its competition from 2016 onwards. It's not finished yet. But what's important is that it resulted into the standardization of 3+1 algorithms, so 3 algorithms that are already standardized as FIPS, and FNDSA, the new name for Falcon, which will become a standard in the months to come, but pretty difficult to standardize. You also have XMSS and LMS that are, as stated before, stateful hash-based signature schemes that have been standardized by the IETF in the late 2010s, and which is now a NIST standard. And also, just to mention, you have all the algorithms that were in the NIST competition that are not that have not been selected to become NIST standards, but that are being standardized either at the ISO or the IETF. And one of them is Frodochem. You may have heard of it. It's a key exchange mechanism that was pushed by the European agencies. Okay, just a word on hybridization. We talked about it in the previous speech too. So many ways of addressing that. If you're at the NSA, American NSA, you're more into this system, right? They state that they are pretty confident in the resistance of MLKM, MLDSA, so no need to hybridize in most use cases. If you're European, you're a bit less pushy, and you said, okay, we have not enough, we didn't have enough time to try and break the new algorithms, and so let's hybridize one traditional algorithm with one post-quantum algorithm, which has incidences on the weight and on the latency it may generate on the network, for instance, because you got to compute 2 signatures, you got to compute 2 key exchange for one operation, but that's for security reasons. Okay, so what's different with post-quantum cryptography? Basically, the baseline is that cryptographic objects are getting XXL, right? Here you have a representation in logarithmic scale of the public keys and signatures of the main signature algorithms. And you can see that before, with elliptic cryptography, you had a great ratio between your public key size and the signature size. If you look at hash-based signatures, okay, you have small public keys, great, but enormous signatures, right? Up to several dozens of bytes. Sorry, several dozens kilobytes, which is enormous. And if you look at modular lattice signatures, there you're more around 2 to 4 kilobytes for the signature, for both the signature and the public key, which is still big compared to RSA and elliptic curve, but it's a good balance between the two. Those ones are very big on the network. It's huge, and this one is the best ratio we have so far. But the NIST is still has still an ongoing competition on short signatures to resolve this problem of size. Okay, and also just to another fact on post-quantum cryptography, we used to have RSA, which was great because it was a one-fits-all algorithm, right? You could do a public key encryption, you could do a signature with RSA. Today, each algorithm has its use case. Okay, so you got to get a lot better at understanding what's your use case, what cryptography you need, and not just rely on one crypto system. Okay, I have to go quickly. This one, okay, just to tell you also that things are moving fast. We have deadlines today, so there's a kind of conversion of statements of the different security agencies that state that you should do your post-quantum migration between 2030 and 2035. Here you have an extract from a public draft by the NIST, which states that after 2035, classical cryptography will be disallowed, which means no more FIPS certification, which means that you cannot, you can no more embark those algorithms in your security products. Okay, and so 10 years left. We're in 2025, so quite there's just a short amount of time to do this transition. Okay, now moving to the challenges in embedded systems, which is the core of my presentation. Okay, so as you all know, the embedded world has specific constraints. One is long lifespan, right? From mere design to end of life. Some products can remain in the field for 20 to 30 years, which is a lot. And so it's really important to take the quantum computer availability as a possibility during this lifetime. The exposition is important too, because you send products into the wild. So if it's in outer space, of course, it's quite difficult to have for a malicious actor to have its hands on the device. But let's say in a car, for instance, it's difficult to have total control over the devices you are exposing in the wild. And of course, physical constraints, and the main ones for cryptography are computational power and memory space. And for all those three constraints, you have things to look at. If you are a vendor of embedded systems, you should look at making your products quantum safe by design today. If you have exposed embedded equipments in the wild, you should look at increasing the resistance against side channel attacks. And at CryptoNext security, we have a library with a side channel resistant version we will look at later. And finally, for the physical constraints, you should look at the memory footprints of the algorithms that are being computed on your hardware. And for that, at CryptoNext, we also have developed a version of the library which is low memory. A version of the library which is low memory, yes. Okay, so resistance against side channel attacks. I see the time is running out, so I'm going to be quick. So no need to look at the mathematical underpinnings. Just telling you about modular lattice cryptography, which is the one we have tested on side channel resistance. It's basically based on the difficulty to find short vectors in lattices. I won't get too far on that. Most of the standardized algorithms today rely on this technology, on this math problem, and one of them is MLDSA, which is the one that we have studied in our case. Advantages, it's quantum resistance, it's pretty performant, and we have a good confidence in the security. Drawbacks, requires hybridizations, and if you're in Europe, it will require hybridization. It produces still large signature compared to the world we had before, and it's relatively new, so maybe new attacks can emerge. Okay, so what we'll do on this algorithm is to try to find secrets thanks to side channel attacks. So what are they? They are attacks that do not have interest into the code itself, but on the observation of physical information emitted during computation. Okay, so two kinds of them are either some executed from a distance, like timing attacks, which are very dangerous, and some require direct access to the hardware, which is the one we will study today, which is DPA. And so how it works, basically the attacker has probes on your hardware, looks at the power consumption during computation, has some traces of the consumption of current, and then applying some statistical tools, you're able to infer some secrets. Okay, and the way to counter this is to mask your code. So what is masking? It's a new paradigm of implementation where basically all your operations and all your variables are splitted into t+1 bits. So if the attacker has t probes, t ways of looking at data in your circuit, you are going to split the secrets into t+1 so that it won't be able to take all the bits of the secrets that are being computed. And so just to show you, it's really a new code, right? Before you had 2 lines, and it transformed into something like more than 50 lines, okay? And that's the only measure, as far as we know, to counter the side channel attacks. And so on this platform with the Cortex M7 CPU, we have been running MLDSA and with our masked version, so resistant to side channel attacks, and we'll see the results that we could infer. Okay, so just quickly, what's important to see is, so the orange line is the state of the art as published at the CHES 2024, and the green line is our implementation. What's important to see is that there's a big increase in the time taken to compute a signature, right? From order 0, so it means no masking, to order 1, you already have a multiplication factor 3. If you go at masking order 4, so all your secrets are splitted into 5 bits, sorry, you have a multiplication factor of 30, right? So it has a big implication on latency. But yeah, we are doing better than the state of the art, so that's great. And also, you need a great random generator, okay? Because you need loads and loads of megabytes of random to make sure that all the little bits of secrets look random, okay? So it's important to see that if your random generator is bad, what you'll be measuring as performance will basically be the random generator overhead and nothing else, okay? So it's really important to have a great random generator on this one. Okay, and a second thing I wanted to talk about was the performance of our algorithms in constrained environments. So here we're talking about hash-based cryptography, not lattice cryptography. And the algorithm we're looking at is SLHDSA, so the stateless hash-based algorithm that has been standardized by the NIST. The good thing is that it's quantum resistant. It doesn't require hybridization because hash-based are so well studied and secure that we don't need hybridization, and we have a high confidence in security. The drawbacks is that they are sometimes stateful. Hopefully, SLH-DSA is stateless. They have very, very large signatures, and they are pretty slow. Okay, we have the same board. We are still computing our algorithm on the Cortex-M7. And that's basically a study we have done for the French national, the French Center for Special Studies, the CNES. Okay, so what do we see? Basically, in orange, you have the software version of the SLH-DSA, and you can see the speed up we are able to gain with a SHA-2 accelerator, right? So for the hashing of SHA-512, we are able to have times 700 acceleration. For the SHA-2 hash chains, because basically SLH-DSA computes hash chains of seeds, right? Well, it's a bit less, even a lot less, which is a little bit disappointing because basically every time your CPU is asking the hardware accelerator, there is a little latency, right? So here you only had one request from the CPU to the hardware accelerator. Here for the hash chain, every time you compute a new link in the chain, you've got to get back to that accelerator, and this is why the results are a little bit less surprising. Okay, and if we're looking at SLH-DSA verification, so basically we are able to have a speed up thanks to the hardware accelerator, a speed up by a factor 3.5 that performs 4 verifications by second, which is not great, of course, but it may be sufficient for the use case of this algorithm, which is clearly made for code signing or root CA. So it's not an algorithm which is made to create many signatures at the runtime. And there is still 20 to 2,000 times slower than ECDSA on this platform, which is quite enormous, right? And still room for improvement with a more accurate software and hardware design. And you have a paper here which is really interesting if you're interested into that topic. And finally, the stack usage. So not so dramatic, right? Here we have the stack usage in green of traditional algorithms, ECDSA and RSA. And here we are about at the level of the ECDSA stack needs. So it's not a real concern here. Okay, and as a conclusion, I hope I'm not getting too away from schedule. So PQC is still a challenge for embedded systems. You've seen that either if you're in the side channel resistant track or in the performance tracks on constrained environments, there is some overhead in terms of performance. The choice of algorithm, parameters, and countermeasures may be adapted to each use case, so we get to all be more and more fluent in the PQC subject. Hardware acceleration, of course, has much to offer, but not always mature on PQC. You don't have accelerators that are designed specifically for post-quantum cryptography today. Anticipation is key, of course. If you have products that are coming in the product line in 1 or 2 years, you should today think about post-quantum cryptography. And one topic I don't have time to talk about, which is a pity, is crypto agility, right? You may have heard of this concept. And at CryptoNext, we are developing a whole structure to help you edit, modify, add algorithms without big disruption on your infrastructure. So a very swift and agile way of changing cryptography without breaking all the code, breaking all the infrastructure. Okay, but that can be a subject for future talks. Thank you very much.
Thank you, Charles. Thank you very much. So now, time for questions. Do we have any questions? Anyone? Yep.
Thank you for your presentation. I caught between the lines you said that SLH-DSA would be more suitable for root CAs.
Yes.
Could you please elaborate on that?
Okay. So as I said, the problem with SLSG, several answers to that. First thing is that SLSGSA produces small signatures, but sorry, I get messed up. No, okay. The first thing is that it doesn't need hybridization, right? So for root CA, it's great because you don't need to have two different algorithms that will sign your root CA. Okay. Second thing, it produces big objects, big signatures. So it's not very suited to have all those huge signatures into certificates that would then be circulate on the network. So it's better to keep that at root CA level or at a firmware signing level, but not stuff that needs to be regenerated very quickly and very often. Okay, so those are the two main reasons for that. And also they are very secure. We know them very well. So for root CA, it seems quite suited.
Thank you. Any other questions? Yes.
So thank you for the talk. Could you show the slide with the hybridization again, maybe?
Sure. I don't know. Yes. Was this one?
Exactly, yes. So I think we talked about the first two cases, but the third case made me a bit curious. What would be the benefit of combining two post-quantum? I think these are two slightly different ones. Okay, I didn't see the difference there. Did you talk about these?
No, I didn't. All right. So today, the public positions of the different agencies are on those two tracks, but we've been hearing little murmurs of this possibility, meaning that if we have trained and upgraded our infrastructure to allow for hybrid schemes like post-quantum traditional, why not keep a hybrid scheme, but this time with two post-quantum algorithms relying on two different mathematical problems? Because we are entering an era of cryptographic disruption, and so it's possible that an algorithm that is standardized today will fall. And so just to prevent that, we have been hearing, but it's not official at all, that some people were thinking of keeping this hybrid track scheme.
All right, thank you.
Any other questions? If not, thank you very much for this very interesting presentation, Charles. Thank you.